Okay, let's unpack this.
Let's do it.
We are standing right on the precipice of a massive technological shift in the enterprise. I mean, for the last few decades, software has been fundamentally deterministic.
Right.
You write a script, it follows a fixed path, and, if it encounters something unexpected, it halts.
It breaks.
It breaks. If you think of traditional automation, it's a railway line, it's predictable, it's efficient. But if the tracks are broken, everything just stops and waits for a human to come fix it.
Precisely. And that era of static, deterministic execution is, well, it's rapidly ending. We are moving from those fixed railway lines to autonomous reasoning AI agents.
And these are operating within your most critical enterprise infrastructure.
That's the key. We're talking about systems that don't just execute code. They perceive the environment, they reason about ambiguity, they plan these multi-step processes, and they execute really complex actions using tools across, financial platforms, CRM systems, internal data warehouses.
And that level of autonomy introduces an entirely new magnitude of operational complexity. So our mission today is to dive deep into the operational reality of these systems. If you, our listener, are an enterprise architect or an engineer trying to tackle how to safely manage this transition, well, this deep dive is your necessary engineering handbook.
Yeah.
We've pulled together a stack of sources that define the specialized discipline required to govern this new reality. AgenticOps.
AgenticOps. It's the industrialized framework for managing the entire life cycle of these autonomous systems. I mean, from the initial scope definition and ethical boundaries all the way to continuous monitoring and eventually, decommissioning the agent.
Mostly to grave.
Exactly. It's about ensuring these systems are not just clever, but that they're also reliable, safe, and cost-effective, especially when they're operating in these complex, regulated environments where the stakes are just incredibly high.
And here is the key insight hook, the thing that really defines the necessity of this new discipline. We aren't just worried about systems being down anymore. Traditional DevOps handles that. A system is down, it throws an error 500, it stops, it's easy to detect. We now need to worry about systems being up but silently failing.
That is the profound governance challenge of agent systems. It really is. A traditional system, it throws an exception, it waits for help. An agent, on the other hand, can continue operating perfectly. It can be throwing all the correct status codes, but it's calculating the correct output based on a fundamentally hallucinated fact.
Wow.
Or it's pursuing a prohibited path because it just misinterpreted its system prompt. That failure is functional and semantic, not technical.
So we need to put the brakes, the specialized airbags, and a high-definition mandatory audit trail onto this autonomous functionality to make it viable in the enterprise.
That's it. That is the core purpose of AgenticOps building absolute trust.
Okay. Let's start by defining what this paradigm shift actually means and why this specialized operational discipline is not a luxury, it's mandatory.
Right. So the necessity of AgenticOps, it arises directly from what our sources are calling the reasoning gap.
The reasoning gap.
Yeah. Think about legacy automation workflows. They operate on these really rigid logic trees. If they encounter ambiguous data or an unexpected format or some edge case they weren't explicitly coded for, they just break down immediately.
They're brittle, they can handle high volume and speed, but they cannot handle uncertainty. They rely on the environment being perfectly structured and predictable.
Exactly. Agentic solutions, leveraging these large-scale reasoning models, they close that gap. They do it by applying cognitive reasoning to navigate uncertainty.
So the system can adapt its plan on the fly.
Right. If one API endpoint is failing, the agent can decide to use a backup data source or dynamically reroute the entire workflow. This flexibility is the superpower we desperately want for enterprise automation.
But it's also the source of the risk.
It is simultaneously the source of this new class of risk.
So the core function of AgenticOps isn't to stop the agents from being autonomous, but rather to, down that autonomy.
That's a perfect way to put it. You need a rigid structure that ensures the agent operates strictly within defined constraints of authority and compliance. You're essentially building guardrails around that powerful flexibility.
That's a critical distinction. And this fundamentally changes the management focus for technology leaders, right? We're moving away from managing the specifics of code, checking syntax, ensuring functions return the right type.
Right, and moving toward managing the system's intent, its capability, and its outcome. We are governing what the system is trying to achieve and what tools it has to achieve it, not the exact script it runs.
That conceptual shift is enormous. And as we said, it forces us to redefine what failure even looks like. Let's delve deeper into that idea of the semantic failure versus the binary failure.
Okay. A traditional failure is easily logged. It's a 404, a 500 error, a runtime exception. The system status is clear.
Up or down?
Up or down. In an agentic environment, the system is fully available. The API calls are successful, they're returning 200, okay. But the agent is failing by making an incorrect, ungrounded decision. For instance, an agent tasked with summarizing customer feedback might flawlessly access the database and the ticketing system, but then hallucinate a summary that completely misrepresents the customer's sentiment.
That is the operational nightmare. You have a system that is functional and fast, but it's subtly leading the business toward incorrect decisions.
Precisely. And this necessity means we have to shift priority away from simple uptime metrics and focus instead on the reasoning trace.
The reasoning trace.
Yeah, we need detailed, verifiable insight into why the agent chose to take the action it did. What was the plan it created? What data did it ground its decision in? Did it respect the guardrails we put in place? The outcome matters, but the chain of logic leading to that outcome matters more for governance.
And if we're dealing with financial systems or customer data, these distributed, sensitive systems of record, this brings us directly to the absolutely non-negotiable mandate for auditability.
Absolutely. I mean, enterprise governance mandates, especially in finance, healthcare, other regulated sectors, they require full traceability for any action that modifies a customer's record or initiates a transaction.
When a human does it, their identity and timestamp are logged.
Right. And when an autonomous agent acts, we need that exact same level of ironclad accountability.
So AgenticOps is not simply a technical optimization to improve speed. It's fundamentally a compliance necessity to ensure the enterprise remains audible and legally compliant in the age of autonomy.
That's a critical distinction. AgenticOps must integrate deep auditability and non-reputable logging into every single reasoning loop.
And non-reputable, just to clarify, that means the logs can't be altered after the fact.
Cannot be denied or altered even if the agent itself is compromised. This is about building total accountability, which we achieve through advanced techniques like cryptographic anchoring, and we'll definitely dissect that later.
Yeah.
But accountability, it really starts with a controlled, rigorous development process.
Okay, so if the move to reasoning agents is the agent development lifecycle, or ADLC, is the how we build that trust into the system. And it's crucial to understand this is fundamental different from MLOps or DevOps. The sources emphasize that the ADLC is continuous and heavily feedback-driven because we are dealing with non-deterministic model reasoning. It's not a straight line.
That continuous feedback loop is non-negotiable. It has to be. Unlike traditional software where functionality is static, an agent's performance can drift over time as its external context changes or as the underlying models get updated. So the ADLC forces rigor and control over this stochastic process. And it starts with defining the mission in the first phase.
Okay, phase 1, design and requirements. When we approach this first phase, where should technical teams be focusing their energy to make sure they get the highest immediate return on investment?
You must focus on high-value use cases with clear, substantial ROI. This means prioritizing tasks that are repeatable, data-intensive, and currently bottlenecked by human intervention or, slow, error-prone manual processes.
So don't start by automating simple data entry.
Exactly. Target complex, high-volume decisions that require synthesizing information from disparate systems and making judgment calls. That's where the real cost savings lie.
And the requirements themselves, they need to be specific and quantifiable. The sources draw a really great distinction here between just vague wishes and actionable objectives.
Yes. Vague goals like improving customer support efficiency. That's useless for an agent. It can't be measured. It can't be validated. The measurable requirement has to be granular and operational, something like autonomously resolving level 1 billing inquiries by updating the account status in the CRM and sending a confirmation email, all while maintaining a customer satisfaction score above 92%.
So you can actually measure that.
You can measure it. And those measurable objectives allow us to define statistical service level objectives, SLOs, later on in the process.
This is also where we define the agent's boundaries and the ethical guardrails.
Correct. The agent's persona is the tone and style of interaction, how it communicates. The ethical guardrails are the hard operational constraints, and they're typically implemented via policy as code.
Give me an example of that.
Okay, take the example of an agent adjusting customer invoices. The guardrail must explicitly forbid it from offering discounts outside approved ranges, regardless of how cleverly a user might try to prompt it to do so. These constraints are the digital equivalent of legal and HR policy, encoded as hard stops in the architecture from day one.
The challenge here, though, it seems like it would be anticipating every single possible failure mode at the design stage. That seems almost impossible for a non-deterministic system.
It is impossible to anticipate every failure, but the design phase sets the philosophical boundaries. It dictates the agent's maximum authority and its minimum security posture. Every subsequent stage construction, testing, runtime, then builds the technical controls to enforce these boundaries that you defined right at the start.
Okay, so that brings us to construction and context precision. This is where we're building the architectural blueprint. What are the essential components that have to be defined in this blueprint to ensure operational stability?
So here you are strategically mapping out the internal modules and the external dependencies. Internally, this involves defining the reasoning engine, that's the core model logic, the RAG pipeline.
Retrieval augmented generation.
Right, how it accesses its knowledge, and the tool calling layer, which is how it interacts with APIs. Externally, you define the knowledge context, what data sources the agent uses for grounding facts, like internal wikis or database schemas, and the tool inventory, the exact APIs and functions it's authorized to call. This defines its entire functional universe.
You mentioned the RH pipeline. Let's pause on that and explain the technical challenge of managing that context. The source material flags context flooding as a major pitfall. What is that?
Context flooding is essentially information overload for the AI's reasoning engine. If you dump too much irrelevant data into the agent's prompt, for instance, providing 50 pages of documentation when it only needs one specific paragraph, three negative things happen.
Okay.
First, the agent loses focus. It often misses the actual constraint or the relevant fact. Second, its accuracy drops, so it hallucinates more easily. And third, latency and cost increase significantly because the agent has to process all that noise.
So if I'm understanding this correctly, the problem isn't a lack of data, it's too much unfiltered data being passed to the model.
Exactly. The expert solution is context precision. It's about dynamically selecting only the most relevant, necessary information for the specific task at hand. This requires some pretty sophisticated filtering and semantic retrieval mechanisms that understand not just keywords, but the intent of the query.
So it's surgical data retrieval, not brute force data dumping.
That's a great way to put it. And this is a crucial engineering task that dictates both performance and reliability.
Okay, that makes the construction robust, but how do we prove it's safe? We move to testing and behavioral validation, and the sources are really clear. We are leaving traditional unit testing behind.
Absolutely. Traditional unit testing, it checks if, function A returns expect output B given input C. But because agents are non-deterministic, we are shifting from testing for a single correct answer to testing against a distribution of acceptable outcomes.
So we're validating its behavior, not its exact output.
Exactly. We're checking if the intent was met safely and within bounds, not its exact output format.
What are the key techniques used to validate behavior in this kind of non-deterministic environment? I mean, we need more than just running happy path scenarios.
Oh, yeah. We rely heavily on adversarial techniques. This means actively employing sophisticated jailbreak prompts. These are inputs designed to try and bypass those ethical guardrails we said earlier.
So you're actively trying to trick it.
You are deliberately trying to trick the agent into performing prohibited behavior, like disclosing sensitive customer data, exceeding its defined authority, or creating an output that violates compliance rules. You run thousands of these synthetic negative scenarios to hunt for those obscure, malicious edge cases.
That sounds like a continuous red teaming exercise built right into the development loop.
It is, and the metrics reflect this behavioral focus, statistical SLOs. Since the outcome is non-deterministic, service-level objectives become probabilistic. We define success based on the probability of a successful compliant outcome over a large sample size of inputs rather than a binary pass-fail.
So for a high-stakes billing agent, the SLO might be.
It might be 99.9% of decisions must adhere to the discount policy, acknowledging that we're managing probability, not certainty.
Got it. Okay, so once it's tested, the agent moves toward production. What are the necessary safety measures, the deployment gates, that keep a potentially flawed agent from going live and causing a widespread incident?
Deployment must be managed via automated pipelines with really rigorous quality gates. For example, an agent cannot be promoted to production if its accuracy score drops below a predefined threshold on a goal dataset, or if its calculated token usage, which is a proxy for cost per task, suddenly exceeds the acceptable budget.
Cost is a reliability factor here.
It is. A runaway cost often signals a runaway reasoning loop.
And phased rollouts are key to managing the blast radius of any failure.
Essential. Using techniques like canary deployments, releasing the new agent to a small, isolated segment of internal users or maybe low-risk customer segments first is vital to ensuring that if a catastrophic, unexpected behavior emerges, the blast radius is minimized. We need to be able to shut it down before it impacts mission-critical systems.
Okay, so once deployed, we enter the outer loop, the continuous monitoring and tuning. This is the stage where the agent learns from its real-world performance.
This is the critical feedback mechanism. We use production logs, the decisions, the errors, the successes, and the human overrides to continuously refine the initial system prompts, update the knowledge context, and even fine-tune the underlying models to adapt to shifting environmental patterns or business requirements.
The business changes, the data changes, the agent has to adapt with it.
But in a controlled loop.
Right. Finally, the formal retirement. Why is this seemingly dull phase such a profound security and governance necessity in AgenticOps?
Because governance demands persistence. When an agent is decommissioned, you have to formalize the process. This involves revoking all associated API keys, deactivating the agent's digital identity in the identity provider, and critically, archiving its entire interaction history. That archiving ensures long-term auditability, potentially years down the line, and satisfies the non-repudiation mandates, proving what the system did and when it stopped doing it.
Okay, so that's the life cycle, but to actually execute this, you need the right architecture.
Right. To reliably execute this rigorous ADLC, autonomous agents can't be built as monolithic applications. They must be structured using a layered architecture that enforces separation of concerns. This is for governance, safety, and scalability. It's the professional standard for enterprise AI implementation.
Let's walk through the foundational structure our sources identify, the 6 architectural layers. Where does the interaction with the external world begin?
At the top is the application layer. This is the presentation layer, right? It manages the user interface, authenticates the incoming endpoints, and captures the initial high-level user intent. Beneath that, we find the system's true central nervous system, the orchestration layer.
Which, as we mentioned earlier, acts as the system's brain.
Exactly. It's responsible for receiving the high-level goal from the application layer, say, process this complex customer claim, and it decomposes that goal into granular subtasks, routing those tasks to the appropriate specialized agents. It manages the complex multi-agent collaboration, handling the delegation and integration of results.
Then we get to the agent layer itself.
This is where the core reasoning, planning, and individual autonomy reside. And importantly, in a multi-agent system, each agent here has a strictly defined scope of authority and a specific, limited set of authorized tools and APIs it can call. This ensures that a failure in one agent is constrained to its specific scope.
But agents, unlike traditional stateless web services, need memory to function effectively. Where does that operational memory and knowledge live?
That is the context layer, and it is critical for maintaining what we call agentic state. Traditional services are often stateless. They forget everything between requests. Agents need both short-term and long-term memory to remember previous conversation turns, the outcomes of prior tool calls, and grounded facts.
And the challenge is that an agent requires specialized storage, not just a standard database.
Correct. It needs storage that supports 2 very distinct requirements. First, semantic retrieval, typically via vector stores, for long-term memory and grounding like recalling past customer interactions. And second, exact state serialization for short-term execution. This is crucial for consistency within a single complex reasoning path.
So if it stops mid-task, it can pick up exactly where it left off.
Exactly, without losing the integrity of its intermediate steps.
Okay. And finally, we have the data layer and the model layer at the bottom of the stack.
The data layer is the enterprise source of truth. It provides the grounded facts needed to prevent hallucinations, and, most critically, it records all actions for those non-repudiable audit trails we talked about. And the model layer abstracts the specific reasoning engine. This separation is key for agility. It allows the enterprise to swap out a large, expensive model for a smaller, cheaper one, or to upgrade to a newer version without having to re-architect the entire control and governance system.
That layering helps manage technical boundaries, but in the real world, a single agent rarely completes a massive enterprise workflow. The sources clearly point toward the necessity of distributing complexity across specialized agents. Monolithic agents they become governance and performance bottlenecks.
Absolutely. The multi-agent approach is the only way to manage large, complex workflows reliably. And we use specific architectural patterns, each with distinct trade-offs regarding speed, cost, and reliability.
Okay, let's start with the most intuitive one, the sequential pipeline pattern.
In this pattern, tasks flow through a fixed sequence of specialized agents. Agent A extracts data, passes its validated output to Agent B for reconciliation, which then passes it to Agent C for final formatting and delivery.
This is very predictable.
Highly predictable, easy to debug, and low latency because the path is clear. However, its major drawback is fragility. A failure at one stage halts the entire pipeline, creating a single, severe point of failure within the flow.
That lack of resilience sounds like a problem for mission-critical tasks. So for more complex goals, we use the hierarchical supervisor pattern.
Right. This mimics a human management structure. A central supervisor agent receives the complex, high-level goal, for example, process a customer dispute, and breaks it down into subtasks, delegating them to specialized agents.
So it's like Agent X, check the billing history. Agent Y, draft a communication.
Exactly. It excels at handling highly complex or ambiguous tasks by intelligently delegating. But the supervisor itself is a single point of failure and a massive latency bottleneck, as every single step has to be routed through and validated by that central authority.
Okay, let's talk about optimizing for accuracy, even if it adds cost. The evaluator optimizer pattern, which is also known as reflection.
This pattern is vital for high-stakes decisions where correctness is paramount. One agent drafts a plan or a response, that's the optimizer, and a separate critic agent, the evaluator, reviews it against a strict set of constraints or knowledge context, suggesting improvements before it's ever executed.
So it's like a built-in peer review.
It is. This reflective loop dramatically increases accuracy and adherence to complex instructions.
Okay.
However, because you are running multiple full reasoning cycles for every single task, it significantly raises both latency and critically operational cost due to increased token consumption. It's the highest quality, but it's also the highest price.
If the enterprise is dealing with multi-step transactions across distributed systems, like updating a financial ledger and creating a customer ticket at the same time, integrity becomes the biggest concern. This is where the Saga orchestration pattern becomes mandatory.
The Saga pattern is perhaps the most essential for enterprise data integrity. It's designed explicitly to prevent silent failures or inconsistent system states. If an agent executes a transaction across 3 different services, the Saga ensures that for every successful step, a compensating action, a rollback, is defined and ready.
So if step 2 fails,
It automatically executes the compensating action for step 1 to restore data integrity.
could you give a specific example of that rollback in action?
Certainly. Imagine an agent attempting to onboard a new vendor.
Okay.
Step 1, create a record in the vendor database. Step 2, allocate an initial budget in the financial system. Step 3, send welcome documentation.
Okay.
If Step 2, allocating the budget, fails due to an API timeout, the Saga immediately executes the compensating action for Step 1. It deletes or marks the vendor database record as pending failure.
And this prevents the company from having a vendor record without an allocated budget.
Exactly. It prevents that inconsistent state that is far harder to detect and fix manually later on.
It sounds like achieving transactional integrity in an autonomous world. That level of engineering effort, defining all those rollback paths up front, must be a huge engineering commitment.
It is a massive commitment, but it is the non-negotiable cost of doing autonomous business in highly regulated environments. You cannot allow autonomous agents to leave your systems in an inconsistent state.
And finally, the fundamental pattern that underlies much of this autonomy, the react loop.
The react reason action loop is the continuous engine of thought. The agent reasons about the current state, selects an action, which is often calling an external tool, observes the result of that action, and then updates its plan based on that observation. This makes the agent highly adaptive to dynamic environments.
But as we discussed, this is where you risk hallucination cascades or just getting stuck in an infinite loop if it's not bounded correctly.
Right, if it's not rigorously bounded by the orchestration layer.
And the necessary mechanism for managing enterprise liability is the human-in-the-loop pattern.
The human-in-the-loop is the final, ultimate failsafe. The agent pauses at critical decision points before initiating a high-risk action like approving a large credit line or deleting production data, and it requests human approval or clarification. It builds immediate trust with the human operations team and ensures safety, though the trade-off is, of course, the immediate acceptance of human-induced latency in the workflow.
Okay, we've established how to design and build these systems, but the real challenge is controlling them once they're running at velocity in a production environment. This next part focuses on those practical engineering controls, the brakes and airbags of the autonomous system.
Right, the things that stop a functional agent from becoming a catastrophic one under load or duress.
Let's start with the mechanisms that protect the downstream services that the agent talks to, especially if the agent starts to malfunction. We use circuit breakers and token buckets.
A circuit breaker is a standard practice, but applied here, it protects downstream systems from an agent that's entered a runaway failure state. If an agent starts what we call a retry storm, repeatedly attempting a failing API call because its reasoning engine hasn't processed the failure correctly, the circuit breaker
It
trips.
just blocks the agent.
It blocks the agent from making further calls to that service for set duration. The circuit breaker's message is essentially, "You are broken, stop hitting me."
And how does that differ from the token bucket algorithm, which sounds like another form of rate limiting?
The difference is subtle, but really powerful. A simple rate limit enforces a maximum frequency, but the token bucket controls velocity and scope. Agents are granted a finite number of tokens at a steady defined rate. Every action, every tool call, every critical database lookup consumes a token.
And if the bucket is empty,
The action is denied until the bucket naturally refills. This mechanism allows for natural, controlled bursts of high activity when necessary because tokens can be saved up, while strictly preventing those rapid, continuous runaway loops that lead to self-inflicted denial of service.
so the token bucket says, you are working, but you must respect the budget. Slow down.
Exactly.
That handles the quick, frantic DOS attacks. But what about the slow, insidious loops? The agent that gets stuck doing the same thing over a long period without violating the frequency limit? You call these slow loops.
That's where pattern-based pattern breakers are essential. A standard rate limit won't catch an agent that gets stuck repeating the same three-step cycle. Query DB, plan response, query DB, over an hour. To catch this circular reasoning, a supervisor component maintains a sliding window of recent actions and inputs.
And it's looking for repetition in that window.
Right. If the supervisor detects the exact same sequence of actions, or querying the exact same database record with the same input parameters, occurring too many times within that window, the supervisor immediately interrupts the reasoning loop and forces a hard reset or a human handoff.
It's actively looking for operational monotony as a sign of failure. That's a huge departure from traditional systems management.
It's about detecting semantic stagnation. We're moving from monitoring server health to monitoring cognitive health.
Moving from monitoring to absolute control, we need hard governance. This demands rules enforced based on the meaning of the agent's actions, not just the code.
This is where policy as code hard stops come in. You use declarative rules to enforce governance based on semantic context, parsed directly from the agent's reasoning trace and its tool inputs. For example, the policy isn't just don't call function X, it's deny any action that attempts to export more than 500 records from the CRM system.
And the system can understand the intent.
The system parses the agent's plan and recognizes the intent to export 501 records and automatically denies the action based on the policy, overriding the agent's logic.
This allows the enterprise to enforce business policy, legal policy, and security policy directly at the actuation level, independent of the model's reasoning.
Exactly. You can also enforce temporal rules, like limiting infrastructure changes to specific pre-approved maintenance windows, say between 2.0 a.m. and 4.0 a.m. If an agent tries to schedule a system update at noon, the policy as code stops it dead, even if the model reasoned that the update was necessary.
When all else fails, when the agent is compromised or fundamentally malfunctioning, we need the ultimate control, the kill switch. This is absolutely critical for emergency response.
You must architect for immediate containment, and this requires two types of kill switch. First, the agent-level kill switch. This is a simple Boolean flag stored in a high-speed, low-latency key value store. Before every single tool call or critical decision step, the agent has to check this flag. If the central control system sets it to OFF, the agent stops its current reasoning loop immediately.
That's fast, but it relies on the compromised agent choosing to respect the check. What about a truly malicious or catastrophic failure where the agent disregards its own instructions?
That requires the system-level or cryptographic shutdown. The agent, as we establish, operates with a verifiable digital identity. It relies on cryptographic certificates for zero-trust communication across enterprise services.
So you just revoke its credentials?
You immediately revoke the agent's identity certificate in the central identity provider. Since all communication relies on verified identities, revoking the certificate causes all downstream services, CRM, financial platform, data services, to immediately reject any request from that agent. This is the fastest, most effective way to isolate a catastrophic agent failure from the rest of the enterprise infrastructure, regardless of the agent's internal state.
All of these controls require that we treat the agent not as some ephemeral script, but as a first-class digital identity with cryptographic verification necessitating rigorous least privilege controls.
This is a fundamental security mandate. You can never, ever grant an agent admin or excessive rights. Access must be restricted to the bare minimum necessary using micropermissions. Instead of granting access to the entire contacts API, you restrict it only to contacts.read and notes.create. If the agent's function is to summarize tickets, it shouldn't have the permission to initiate a wire transfer.
And the concept of just-in-time authority ensures those micropermissions aren't even persistent, which further minimizes the risk.
Correct. High-privilege permissions, like the ability to modify a financial ledger, are granted only for the duration of a specific defined task, say, for 60 seconds while processing a specific invoice. That micropermission is automatically revoked the moment the transaction is complete. This severely limits the window of opportunity for exploitation via prompt injection or if the agent were otherwise compromised.
This level of control demands absolute transparency in the accountability chains. If a bad action is taken, we have to be able to trace it back to a verifiable source.
Absolutely. Every agent must be tagged with ownership metadata, linking it back to a human owner or a managing team. Furthermore, when an action is taken, the audit log must record the entire delegation chain, starting from the original human user request, if there was one, tracing through the orchestrator that decided which agent to use, to the specialized agent that executed the task, and finally to the specific tool call. That chain is vital for forensics, post-incident analysis, and regulatory compliance.
So if AgenticOps is the engineering rulebook and the controls are the safety mechanisms, observability is the lens through which we read the results and detect failure. Standard metrics like CPU usage or memory are entirely insufficient here.
Completely insufficient. We have to move toward reasoning observability, capturing the internal thoughts, the plans, the tool calls.
We need to see what the agent was thinking in order to determine if the failure was technical or semantic. And this requires a standardized way of logging, which the sources call the canonical agent run event.
This structured telemetry schema is crucial for auditability across diverse multi-agent systems. Every step the agent takes, whether it's reasoning, calling a tool, or observing the environment, must emit a structured event containing specific, mandated fields that allow for analysis and compliance.
Okay, tell us about the most critical fields needed for tracing and accountability across multiple systems.
For end-to-end correlation across the entire enterprise, you need the trace.id and the span.id. The trace.aid is the unique identifier for the entire high-level request, so the full customer claim process. The span.aid is the unique identifier for the specific reasoning step or tool call within that process.
So these IDs are how we stitch together the agent's full journey, even as it bounces between different microservices and systems.
That's how you do it.
And to understand where the reasoning loop broke down.
We use the step.type field, which defines where the agent is in that React cycle: plan, tool call, reason, or observe. This field allows forensics teams to pinpoint exactly where in the internal logic a failure occurred. And crucially, the events also capture governance metrics like policy. Result, did the guardrail check return allow, DNY, or flag? And semantic metrics like grounding.status, which asks, was the output validated against known facts in the knowledge context?
Don't forget the efficiency flag, the cost metric.
Absolutely. The usage.tokens field is vital. Token consumption is a direct proxy for cost and computational complexity. If an agent suddenly starts consuming 10 times the number of tokens for a routine task, that is a clear efficiency flag indicating reasoning drift, context flooding, or a subtle, slow-loop failure.
For high-compliance environments, though, we need more than just standard log files. We need verifiable audit trails that are truly non-repudiable.
This is where cryptographic anchoring becomes necessary. Each canonical agent run event is hashed, and that hash is cryptographically linked to the previous entry, forming a continuous, unbroken hash chain. Periodically, the latest head hash is written to an immutable storage system. This mathematically proves that no log entry earlier in the chain has been tampered with or altered after the fact.
And to address the security concern, how do we ensure a compromised agent can't just erase its own tracks or falsify its records?
You do that through the architecture of sidecar logging. Agents are forbidden from writing their own logs directly to the audit store. Instead, they emit their events to an isolated audit sidecar component that runs in a protected boundary. This sidecar handles the hashing, the signing, and the writing to the immutable store. This separation of concerns creates a hard security boundary, preventing a compromised agent from achieving audit log tampering.
Okay, now that we know what to monitor, let's look at the unique kinds of failures we're hunting for. As we established, failure is often silent, incorrect behavior while the system appears to be running just fine.
The most dangerous are reasoning failures. And the primary concern here is the hallucination cascade. This is where a single fabricated fact in an early step, for example, the agent misidentifies customer ID 12324 as 4321, leads the agent down an increasingly incorrect path.
Give us the breakdown of that cascade. How does that happen?
Okay, step 1. The agent misreads the incoming prompt and retrieves the wrong customer ID. Step 2. It uses that incorrect ID to query the financial system, and it finds that customer 43281 has a massive overdue balance. Step 3. The agent then logically determines that the original customer, 1234, must have their service suspended, and it successfully executes the suspension tool call.
So the logic was sound, but the foundation was fabricated.
The agent's logic was sound, but the initial ID was fabricated. The result is a sound action applied to the wrong target. This is incredibly hard to catch without the reasoning trace. And this is closely related to infinite reasoning loops, where the agent gets stuck going from thought to action to observation because it lacks a defined termination condition.
What about failures related to the knowledge base itself?
Those are context and memory failures. We already discussed context flooding, where irrelevant data masks the constraints or relevant facts. We also encounter siloed context, where the agent can successfully see a billing issue in System A, but lacks the full picture because it can't bridge that information to the customer support history in System B.
So it knows a fact, but not the critical context around it.
Exactly. And that leads to a poor decision.
And when the agent starts acting on the world, we worry about actuation failures, failures in the final execution of the plan.
The worst of these is silent data corruption. This happens when a multi-system transaction fails halfway through. A payment record is created in System A, but the subsequent update fails in System B. Without the saga pattern and those compensating actions, the enterprise is left in an inconsistent state. Right. Because no service is technically down, the corruption is silent until it's discovered much later.
And we also worry about self-inflicted denial of service.
Right, often caused by those runaway retry loops, overwhelming internal services, and exhausting API quotas.
And finally, the two major security threats in the agentic world: prompt injection and privilege escalation.
Prompt injection is where malicious or cleverly crafted input overrides the agent's fundamental system instructions, potentially tricking it into disclosing sensitive data or taking an unauthorized action. Privilege escalation is where the agent, using its reasoning capability, exploits a subtle flaw in an API gateway or an internal system to gain access to resources it shouldn't have, sometimes even leveraging its own micro-permissions to trick the system into granting broader access.
Which underscores why least privilege and just-in-time authority are so essential as defensive layers.
They're absolutely essential.
When failure strikes, and we need a military-grade, documented, structured incident response. The traditional incident response runbook is insufficient here.
It requires a specific four-step approach tailored for autonomous systems. Step 1 is containment. Immediate action is paramount, triggering the system-level kill switch and revoking credentials. You have to stop the bleeding instantly and isolate the malfunctioning identity.
Then we move to step 2, forensics.
The primary goal here is data capture. You need to extract the full trace, history prompts, tool calls, model outputs, semantic metrics immediately. And crucially, you must also capture the exact version of the grounding data and model parameters that were used during the incident. You have to know precisely what the agent was working with when it failed.
Otherwise, root cause analysis is impossible.
Impossible.
Step 3 is remediation.
Remediation involves executing the compensating actions, the saga rollback, if multi-system integrity was compromised. And critically, you immediately update the guardrail policies and the policy as code to explicitly block the specific failure path that was encountered. You use the failure to harden the system immediately.
Which leads to step 4, postmortem and tuning.
The entire incident scenario, the prompt, the sequence of actions, the ultimate failure, is immediately added to the adversarial test suite. If this failure mode can be triggered once, it can be triggered again. By incorporating it into the automated testing, you ensure that future updates, prompt refinements, or model changes cannot reintroduce that same vulnerability. This is the mechanism for continuous learning and hardening.
This entire system boils down to continuous assurance, and we have to measure it accurately. What are the key performance indicators for measuring AgenticOps success?
Beyond standard technical metrics, we focus on reliability and governance. Reliability is measured by the task success rate, the percentage of tasks completed end-to-end without human intervention, and the hallucination rate, which must be rigorously tracked and kept below 1% for regulated high-stakes workflows.
And for governance and security performance.
The policy denial rate is crucial. This measures how often an agent attempts an action that is blocked by the policy as code constraints. If this rate is high, say above 5%, it indicates poor agent design. The agent is constantly bumping up against its constraints because its intent or context wasn't sufficiently clear during the design phase.
And for security.
For security, the key metric is mean time to detect, MTTD. For high-severity events like a successful prompt injection attempt, the organizational goal must be detection in less than 5 minutes. That speed is paramount for effective containment.
This brings us full circle. This entire discipline is designed not just to ensure agents work, but that we can prove they work safely and accountably to the business, the auditors, and the regulators. So, what does this all mean? We've covered a vast, complex landscape here, moving from managing static software to governing fundamentally autonomous entities within the enterprise.
AgenticOps is the essential discipline for this new era of intelligent automation. And we've established that successful, accountable implementation hinges on 3 critical pillars working in concert. First, autonomous orchestration.
Which means using sophisticated multi-agent design patterns like Saga and Evaluator Optimizer to distribute complexity and manage data integrity across distributed systems.
Exactly. Second is runtime supervisor controls. These are the essential, non-negotiable safety nets.
Right. Including token buckets to limit velocity, policy as code for those semantic hard stops, and the all-important cryptographically enforced kill switch for immediate containment during an emergency.
And third, end-to-end observability. This is about capturing the reasoning trace via canonical structured events, using cryptographic anchoring and sidecar logging to create transparent, non-repudiable audit trails for every single decision made by the system.
For you, the learner, understanding AgenticOps means recognizing that the next generation of automation requires an engineering handbook focused not just on being smart, but profoundly resilient and accountable, treating agents as complex, first-class digital identities with granular, just-in-time micropermissions is the only way to maintain operational integrity at enterprise scale.
The source material frames this technical discipline as the core differentiator for successful AI transformation. If autonomous systems are going to handle mission-critical workflows, the ultimate question is not if they can make complex decisions, but whether we have built the system of governance and auditing around them that allows us to trust those decisions absolutely. Without the rigor of AgenticOps, that level of trust is simply impossible to achieve and scale. The challenge moving forward is applying these principles without allowing the complexity of the governance itself to stifle the innovation the agents are meant to deliver.